Thank you all for coming. Today's DTM seminar is going to be given by Steve Shirey. We invited the Pope instead, but he was otherwise occupied for today, so it's unfortunately he can't be here, Steve. He sends his regrets. Steve has been a staff member here for going on 30 years now, maybe even longer than 30 years.
I'm wearing my 30-year pin right here.
30-year pin. He came to DTM as a postdoc from State University of New York in Stony Brook, where he did a lot of the early work in understanding and applying neodymium isotopes to the genesis of early continental crust, particularly in Canada. He was just in the same field area with our postdoc Marianne Garçon last summer, looking not at the igneous rocks, which is what he did his thesis on, but all the little detritus that was weathered off of igneous rocks that are no longer there. So he's continuing his path to understand the origin of continental crust. Along the way, while at DTM, Steve's done a number of innovative analytical technique developments, including work with the rhenium Osmium system that's used for not understanding continental crust so much as the part of the mantle that's stuck underneath the continental crust. And part of that work has been looking at very detailed studies at these little inclusions in diamonds that we'll be talking about today. And I think the most fascinating part of this work to me is the ability to use 50 micron inclusions inside diamonds to understand things of a scale of the dynamics of the Earth's interior, 6,000 kilometer, 4 billion year type events. So it's a long extrapolation, but it's done very well, and it's the best evidence we have for looking at the deep mantle. So Steve Shirey will be talking about super deep diamonds, windows on mantle convection, and recycling.
Thanks, Rick. I am really sure the Pope did not get an introduction like that. I know that for sure. But when you go to Goldschmidt conferences, you look right away at the program, and there's a slot. There are time slots across. The first thing you check is to be sure that you're not against some heavy hitter. I was really glad to find out the Pope was talking at 10. Anyway, I'm going to talk about two things today from our diamond work. I'm going to focus on super deep diamonds, and I'm going to talk about the latest evidence we have for recycling in the mantle and kind of the path of recycling. And I'll talk about what these inclusions might show us about the water content of the deep mantle as maybe derived from the slabs that bring the water down. So keep those two sort of things in mind. If you look up here, you see in the background a very kind of chaotically zoned or growth pattern in cathodoluminescence here of a diamond plate in a super deep diamond. And that's very typical of the kind of weird polygonal or almost non-patterned growth textures that you see in some of these diamonds. Let me talk about collaborators here. Eric Howery's idea was it's really his idea to look at the water content of these inclusions with the type of NanoSIMS techniques that are special to DTM. And Karen Smith is a postdoctoral fellow here. She's not here right now, but she's been funded by the Gemological Institute of America, and she chose to spend about a year of her postdoctoral funding down here working on some of these super deep inclusions and other diamonds of her own, and I'll talk about some of her latest results. And then, of course, many of the specimens I'm looking at are historic, and Andy Thompson is one of Mike Walter's Ph.D. Students who've done a lot of work on the inclusions, on the diamonds that I'll talk about today, and this comes from a suite that's provided by Galina Bulanova and her husband Chris Smith, really when they worked at Rio Tinto. Rio Tinto gave them carte blanche to work on a large number of diamonds, and they brought them with them to Bristol. So let's look at super deep diamonds and define what they are. What are super deep diamonds? They're diamonds that form underneath the lithosphere in the convecting mantle, and we know that they're super deep because they have high pressure mineral inclusions in them, and I'll talk about how we know that in a little bit. But so keep in mind that we have two kinds of diamonds: those that are formed in the lithosphere at depths above the lithosphere, asthenosphere boundary here, and they're formed in this region of the mantle that's probably actively convecting. And what I'm showing here in the block diagram, of course, is the pattern of crustal growth that we see on the Earth, where we have old core material of ancient crustal material with its attendant mantle keel that's approximately the same age. So the other feature, in addition to depth, is antiquity. Typically the lithospheric diamonds are much older, we think, than these super deep or convecting mantle diamonds. Now, there's no question that we have recycling into the transition zone of the mantle. Here's a paper by Vander Hilsten and his students and co-workers, well-known figure. But just to remind us that we have seismic evidence for recycling of slabs into the transition zone, this portion of the mantle right here. So there's no question that we should be looking for the process that verifies the seismic picture and also what the chemical effects are of bringing material down with slabs into the transition zone. And that whole picture there in seismology is reinforced by old data that we've had for a long time on the carbon isotopic composition of sublithospheric diamonds. So if we look at the right panel here, here are sublithospheric diamonds or super deep diamonds, and focus on this gray pattern here, which means diamonds that are thought to carry inclusions from the lower mantle. They have mantle-like values in carbon isotopic composition, whereas the transition zone and upper mantle diamonds, those that are above the top of the lower mantle, carry this signature of very isotopically light carbon. And this pattern is very akin to the signature we see in lithospheric diamonds, where we have pyrrhotitic diamonds here that have mantle-like carbon, but in eclogitic diamonds, things that look like the recycled basaltic material, they carry the fingerprint of this very light isotopic carbon, probably derived external to the deep mantle by virtue of the difference between the mantle and this isotopically light tail here. So we'll look at that. Let's look and see where we find super deep diamonds. Here's a map that I've shown in many talks before. Distribution of the continents, and the oldest regions in the center of the continents, the cratons, are shown in brown. And the regions that are built up around the cratons, kind of like a zoning onion skin pattern, are shown in a darker yellow. And the super deep diamonds occur, as brought up by kimberlites that bring up lithospheric diamonds. And they don't occur in every craton, but they occur in the same general old craton pattern as lithospheric diamonds. So you see actually here significant localities in Canada here in the Slab craton, and just below the Slab craton in the ray. You see it here in the Amazonian craton here in South America, a little bit in the West African craton that wasn't once connected, and some in the Copball craton, and over here in Australia. And we're going to focus today on super deep diamonds from a very famous locality called the Juvenile locality here in the Amazonian craton. There seems to be the world's best locality for super deep diamonds. So here's Juvenile. Here's a map of South America, and here's the Amazonian craton split into two halves by the river basin of the Amazon River, and we're going to focus on the southern part here. Juvenile area is right in this region here. And there's two localities where kimberlites are exposed, Collier 4 and Juvenile 5, and these are the only two kimberlites that have actually been found in place on the on this part of the Amazonian craton. There are many, many other kimberlites probably in the region, maybe 20 or 30, but they're buried, and they provide diamonds through river systems that are called alluvial diamonds. And so there's a lot of diamonds found here, but only two localities where diamonds are found in place at these two kimberlite pipes. A significant aspect of the geology here is that the continental lithosphere translated over a plume, the Trinidad plume, around 120 million years ago, and you can see that kind of story over here. Well, that's part of the interesting tectonics we'll talk about at the end. Now, diamond mining in Brazil is really simple relative to other areas. You basically dig a pit in very, very weathered soil here, fill it with water so you get a slurry, and then you muck it up and stir it up like this, like a big bowl, and then you throw it into a concentrator system as a slurry, and out comes concentrate bags of ilmenite plus heavy concentrate that includes diamonds. And then you run this stuff through a Sortex machine, which uses X-rays to fluoresce the diamonds, and then the diamonds are sorted out by automatic methods when the fluorescence is detected. And you end up with cups full of diamonds from this kind of stuff. And anybody can do it, including farmers. And in fact, wherever we went to get diamonds, we actually have joint operations where you have a cattle farmer, and on the side he has a diamond sorting operation. And you can get a lot of diamonds this way. They're not very good diamonds. They're kind of ratty looking, and you'll see that in the next picture. But before I get there, let me just talk about a few geochemical aspects of superdeep diamonds. They're typically rare. They make up less than 5% of the global diamonds. They're irregular. Typically a non-euhedral morphology is seen. They have this complicated internal structure that's evident in cathodoluminescence. And they're often, almost always type 2 diamonds, meaning they're very, very low nitrogen. And we don't know if they're younger than lithospheric diamonds. And we also don't know why they're typically very low nitrogen. And then they often have this tail of isotopically light carbon. So here's Andy Thompson's 80 diamonds he looked at for his PhD thesis. And you can see that here's the mantle here at -5. This is del 13 carbon. Most of the diamonds he looked at are, between -20 and -25. That's pretty amazing. Now, if you make a diamond plate, you see these little flakes in here, these little specks. And so here's a diamond plate that was made by Galena, and there's a bunch of little specks. And her normal mode for analyzing these grains is to sequentially polish down through the diamond. When she sees something interesting, she stops and we study it. And the plate may go on being studied for 5 years and be passed around to various people. And in fact, I'll show you data we have from one plate that we kept in our lab for 4 years, waiting to get the blanks down low enough to make the analysis. What these little flakes are in between, amongst the diamond here, are retrograde assemblages, multi-mineral assemblages at low pressures that when you recombine them make up the high pressure phases that you find at depth in the mantle. So you see all kinds of multi-phase assemblages here, spinel, nepheline, and sulfide. Here's calcolite and spinel. Here's some sodium phase and spinel. Here's orthopyroxene, ulospinel. These are not high pressure phases. These are the low pressure phases exolved at low pressure from the higher pressure equivalents. And so you have to put them back together as best you can to get the high pressure mineralogy. Now, in a really interesting paper that Mike published in 2011 with a bunch of us in Science, he got a really great suite of inclusions that included diamonds that included inclusions of calcium perovskite, magnesium perovskite, calcium ferrite, and this what's called the new aluminum phase, and stishovite. And if you actually look at the suite of assemblages where they would be stable, they have to be under this region where clinopyroxene and garnet, the majoritic form, break down into these different high pressure assemblages. And so Mike made the case in this paper that this suite of diamonds is one of the first that had formed from the top of the lower mantle. And the interesting thing is that these bulk compositions, I won't go into this here because it's in the paper, look like basalt mineralogies that have been recrystallized at these very, very high pressures. And so this is the first instance of recycling that goes down into the top lower mantle. Now, part and parcel of this work was very seminal work that Steely did to demonstrate what these minerals are. Because a lot of the people that reviewed the paper said we need to have some independent confirmation of the mineralogy of these, not just bulk composition. So Steely was able to take these little tiny grains. Here's 10 microns here. So this grain is a multi-phase assemblage. It's only 10 microns across. And here it is here. And go in with his confocal Raman and actually verify that the mineralogy that was identified by Mike and co-workers is exactly what is said. And so this is a bit of an advertisement for the kind of capability here at Carnegie and the kind of collaboration that goes on between the Geophysical Lab and DTM when we have the science need. And Steely graciously gave a ton of time to do this work. You can see it's pretty detailed and very complicated because what happens is when these phases are probed with electron microprobe, even the activation volume that's made by the electron beam, we think of the probe as being non-destructive, but it is destructive for Raman. And so Steely had to work very hard to get around the edges to get away from areas that had been beam damaged by the electron microprobe. So the story we get from this particular suite is recycling of slab material, calling oceanic lithosphere here, down to the top of the lower mantle, and diamonds grow at these depths and take in mineralogies or compositions that actually form the high pressure equivalent of these basaltic composition minerals. They're brought up by a plume and then retrograded into the low pressure assemblages and then delivered to the surface by a kimberlite. And in confirmation of these particular diamonds that carried the basaltic mineralogies, 4 of the 6 of them are very isotopically light in carbon. And that is suggesting that the carbon has perhaps an organic component from the seafloor where there is abundant isotopically light carbon available if it can get down through the subduction system into the deep mantle. Now, one of the diamonds that we had as part of the suite is called J1, and for some reason every diamond in this area is called J something, even if it's from Juvenile or Collier 4. It gets extremely confusing. So this is diamond J1 from kimberlite Collier 4, and here's the diamond, and you see this really honking big sulfide sitting right here with a zone around it of fracture that happens when the diamond is brought up to the surface. Here's a close-up of the sulfide here. And Galena had saved this for us, and we were smart enough not to analyze it to begin with. We waited and waited until we had our blanks down just fine. Because this sulfide sits here in the middle of this diamond. Here's the plate. It also has a perovskite on the backside and a majorite here. And I'll talk, these 2 minerals were studied in a paper in 2009 by Mike Walter and his group at Bristol, including Galena. And but here's the catholuminescence. Here's the perovskite, the hole where the perovskite was after it got ion probed. And here's the majorite on the other side, and here's our sulfide. And you can see what we have in this particular diamond is basically a ratty exterior that's not very nice looking. Here's some holes or regions that have been worn away or percussed. And interior zoning pattern is not as chaotic as some of the sublithospheric diamonds. But it's not a very a great looking zoning pattern to begin with. You see this this crack here, and then here's another, who knows what this phase is in here, but it's not a high pressure phase. So looking at the perovskite and the majorite from their paper in 2009, Mike came up with this really interesting model where the perovskite is extremely high in trace elements. So here are your normal lithophile trace elements. This is times primitive mantle. So the perovskite itself has between 1,000 and 10,000 times chondrites in some of the lithophile elements. Extremely, extremely high. And from this trace element pattern, he proposed that the source fluid for these diamonds actually started as a carbonatite, which was a very novel suggestion at the time. And he actually came here in 2010 or 11, something like that, and talked about this model in detail. This is the same diamond, okay? And then the majoritic garnet has this high pressure partitioning of aluminum and chrome versus silica, which has been used as a geobarometer. And this is a minimum pressure that probably starts at a much higher pressure, and this is the final pressure of equilibration before the thing is brought up by a kimberlite. And this is about at the base of the lithosphere, which is probably where the diamond was picked up and transported to the surface. Now, significant to the later part of the story, and I'm going to show you in a second, is the eclogitic composition here of the majorite garnet. This is the diamond J1 majorite, and you can see it falls very square in the eclogitic field, which means it's got affinities with recycled basaltic material at high pressure. Okay, so Karen and I started working on this inclusion, and it came out in one piece. And is Margaret here? Margaret Merchant here? No. Margaret was here this day, you know, talking to people on campus, and she had a free moment in the afternoon. So she was actually in the room when we broke this out, and we were very surprised to see that it's not actually looking like a sulfide. It's kind of black on the outside, which we'd never seen before, and we were immediately kind of suspicious. Karen went over and put it on the SEM, and here's the maps that are significant. So here's carbon on the actual film that we placed the grain on. Here's the sulfur and iron map, and lo and behold, there's oxygen in here. You shouldn't have oxygen in a sulfide, and this is oxygen in this particular grain. Well, I got all excited and thought we had an iron, some iron hydroxy sulfide, and could we have this at high pressure? And I called up Dan Frost in Beirut, and I said, could we have this? He goes, well, I don't know, this sounds really interesting. Turns out, we took it over to the Raman. Steely did the surface, and it's actually hematite and magnetite and alteration. So we got extremely upset about it, because that meant that our only grain was probably really compromised. So we sent it to Padua, where there's a group that involves Ross Angel as a former geophysical lab postdoc, and they do nothing but work on diamonds and the relationship of grains in diamonds to the external diamond, crystal structure. And so they're very quick at doing this kind of stuff. So we took the grain, put it in super glue, threw it in a slide, sent it over by FedEx. And Fabri Nastola, who did this work, determined that the entire grain is pyrrhotite. And here's the pyrrhotite cell parameters, and for an 11T poly type of pyrrhotite. And the sulfide from this diamond J1 has virtually identical cell parameters, which is amazing considering that this work was done here 40 years ago in some other lab with some other X-ray diffractometer. Fabri gets virtually the identical thing. It turns out to be Fe10S11, which is, you know, breathe a sigh of relief because that's a mantle phase. That's not a secondary phase, and there's only less than 1% perhaps of this alteration. So
Steve, was the oxide you were just talking about just a surface?
Turns out it's just a tiny, tiny surface coating, and the bulk composition of the crystal is entirely this thing, except for the tiny surface. So we went ahead, and Karen and I did the chemistry on it, and it turns out to be eclogitic. This is a ternary diagram of iron, nickel over here, and sulfur up here. And what you see is basically it's in the field. This is called MSS, which means monosulfide solid solution. At high temperatures, you have a field where nickel is dissolvable in the sulfide, and then it crystallizes out at lower temperature. And this is right smack dab in the eclogitic field of where we would expect, you know, an iron sulfide like an eclogitic sulfide from the mantle to be. That's all very good. We're doing the osmium on it. We did the osmium on it, and here's a plot of rhenium in parts per billion versus osmium in parts per billion. This is a slide we've shown a lot of times, and what helps us understand is the composition of this grain relative to other eclogitic and pyrrhotic sulfides that you see in mantle inclusions in diamonds. So the grain from J1 is here, and the field for normal eclogitic sulfides that we've analyzed over a number of years at Carnegie and elsewhere is in the white here. And if you go to lower and lower rhenium-osmium ratio, you move in this direction here, and I've got lines that show the rhenium-osmium ratio at 100, 1, and 0.1. And what this is telling us is that this is as low as any sulfide, as almost any sulfide we've analyzed, and typical of the kind of sulfides that you might see associated with mid-ocean ridge basalt type of basalts. Things that are fairly evolved, have low osmium, have an extremely high rhenium-osmium ratio because they have low osmium. And it also gives us a challenge analytically because you can see that the concentration is about less than 10 ppb, which is not a big deal if you have a rock, but we have a single grain that's only a couple hundred microns, and so 10 ppb at a couple hundred microns is analytically difficult to do, and much harder than if you have something that's what we call pyrrhotic and much higher osmium with maybe 1,000 times more osmium in it. So here's the rhenium-osmium isotope data for this particular grain. Now we got it back from Fabri and it had been broken into two pieces just in handling, which is not unusual. And so Karen did the chemistry on each piece, and then we had some issues with chemistry, and she did a recombination just to see what happened if we had compromised it with the surface coating and that kind of thing. But the point is, these two pieces fall here at very high rhenium-osmium ratio and very high osmium isotopic composition. So this is a 187-188 ratio of like 6. Now, we knew all along that we would have this problem. We have one grain, and if it's not pyrrhotic, how do we interpret this information? How are we going to make sense? What does this tell us about the history of this grain? It's just sitting there up in radiogenic la-la land with very high rhenium-osmium ratio and very high osmium isotopic composition, and it doesn't tell us very much about where it came from. Well, the interesting thing is you can regress these data, or you can draw a line between these data and where the mantle should be, which is this line down here, where we call it convecting oceanic mantle, which would be around 0.13 or 0.127, which on this scale is a little tiny region right here, and a rhenium-osmium ratio of 0.4. So So it's way down here at kind of almost the origin. And so a line like that has a 650 million year age, and this point here turns out to be a data point that that came from an abstract given, a talk given at the 10th International Kimberlite Conference in Bangalore, India, by Mark Hutchinson. He had one Juvenile sulfide that he'd analyzed with Graham Pearson's old lab at Durham, Jeff Knoll and Chris Dale. And that, on this scale, is almost where the mantle is. It actually is a precise enough analysis. If you blow the scale up, this is actually higher than the mantle and would give an older age like that. But on this scale, it's not inconsistent with the idea that at least these sulfides that are floating around in the mantle in this particular diamond are 650 million years old. The uncertainty on this age, this model age, if you put an envelope around these error bars here, would be about 150 million years. So the interesting thing is, here's the diamond. So here's our sulfide. It's here with 650 plus or minus 150 MA, age determination, model age. The perovskite is out here. Now, interestingly, in the paper in 2009, Bulanova and crew had this done on the ion probe at Edinburgh, the perovskite, and they got 101 MA age, which is about the age of kimberlite eruption. And so what we have is the potential for a diamond that has an old piece of material in it that it captured from the mantle. We don't know the age of the diamond per se, but it has to be younger than 650 and older than 107. And this typical rim growth suggests that this diamond has had a complicated history and incorporated mantle phases maybe on the outside at a time maybe after the formation of the interior part of the diamond. Now, that's not supported by any zoning here because we don't see any zoning pattern that shows us a period of resorption or growth in the mantle, but that's at least one possible interpretation. So what this means is that we need to do a lot more diamonds that have sulfides if we can find the sulfides, because if you look at what's going on in the mantle, if you want to look at a tectonic model for this region, this is from a paper by Ben Hart and Steve Richardson, who's visiting us on sabbatical for the next month and a half. Been here for about a month. But Ben and Steve hypothesized, based on majoritic garnets that he's analyzed from Juvenile, and I'll talk about those in a second, that when you put together Gondwana like this with subduction system off to the northeast, that a slab comes down like this, brings material down into the top of the lower mantle, and a plume coming up picks up material from this particular slab, brings it up with carbonatitic type melts, and sticks it into the Amazonian craton. And if this is true, this 650 million year age is external to this system. So it's either a sulfide from the slab, and it would be an older slab, or it's a sulfide from the surrounding mantle that's picked up by the system, the tectonics we see here. Part of the story is also shown by Steve's analysis in the neodymium and strontium isotopic composition of majoritic garnets that look very much like ambient mantle. The age resolution on this, there's no real age resolution on this, but we simply see consistency with the idea that sulfide could either be from slab components or from the surrounding mantle. So with that, I'm going to shift to, with a little bit of a précis on what these kind of results show us about mantle convection in this region. I'm going to shift to the story about water, because I've given you the system by which we bring water into the deep mantle, how the slab comes down, and what the age constraints are on it. And then the question is, how much water can the slabs bring down? Here's a summary diagram from Mark Hirschman's 2006 annual reviews paper, and it's Mark told me at the Volatiles conference a week ago that this diagram gets reproduced all the time. He's always a little bit embarrassed because it's a little bit too simplistic, but I think the point is made very well in its simplicity. The transition zone here is the region we would expect to be very capable of holding a lot of water. And so these super deep diamonds are the best way maybe to probe, or one of the best ways to probe how much water could be there and what the carrying capacity of various mantle phases are. So we'd want to know what the activity of water in the deep mantle in the diamond forming fluids might be. You know, if they're coming from carbonatitic type material, is the activity really low? Just can we in the end back out what the wetness of the transition zone is? And more importantly, can we confirm that slabs deliver water, and in what minerals? Are they in the minerals that we think? So we're ideally suited at Carnegie to do this kind of work because of the NanoSIMS here. And here's the DTM NanoSIMS going to be showcased tonight, right, I guess. And Larry Nittler has written software for it, mostly for his analysis and the finding of grains, pre-solar grains that have an unusual isotopic composition. But Eric hit on the idea that this rastering software that Larry wrote is ideal for looking at water in these kind of complicated exolved assemblages in super deep diamonds. So I'm showing in this slide kind of how we do this work. This is all Eric's development work. I mean, I kind of sat beside him, but you know, he's the master, and so I wish he was here to hear this. But I mean, basically, what we do is we take a grain. This is flipped, so if you see the labeling is backwards, I flipped it so it matches the NanoSIMS, and we've got a Majorite here with a carapace of clinopyroxene. So this clinopyroxene is exolved as a component out of the Majorite at lower pressure, and in a normal SIMS analysis, a secondary ion mass spectrometer analysis that you see like on the 6F or on the 1270 or the 1280, you have a pretty big beam. And the NanoSIMS, you've got a much smaller beam. It allows us to raster over an area like you see in red here, and then put together a picture of where the water is coming from. How much is coming from the pyroxene, how much is coming from the Majorite. Now, a problem with the work is that we don't have good standards. For ion probe work, you need really good standards, and the problem is you can't get high pressure phases that have been made with a known amount of water. And so if you use pyroxene, let's say the water content of terrestrial pyroxenes, they're low pressure pyroxenes and they have much less water than you would want, than you could put in them. And so here's Eric's calibration curve for pyroxene, and it extrapolates up here to a very different value than if you take a glass and you put a known quantity in the glass, and it extrapolates to a lower value. So we have an inherent fairly large uncertainty due to the calibration problems, and so in all these calculations I'll show you in subsequent slides, we're using the more conservative lower water contents from the glass calibration, because at least that's in the range of water content that we see. Now the nice thing about this particular technique is you can look at any phase you can get under the ion probe beam. So instead of having to find a very special, unique grain, any grain that you can get into a polished diamond plate can be looked at. And so this is quite a few inclusions that have been looked at. We've got bridgemanite, clinopyroxene, ferropericlase, coesite, Majorite, calcium perovskite, calcium silicon titanium perovskite, spinel, and the new aluminum phase. And the water contents that we've obtained are here. And a lot of this variability is not ion probe uncertainty, it's actually geological uncertainty. And if you have a number of grains, they don't always have the same water content, they're from different diamonds. And so what I'm going to show you is the grains we sort of understand something about and can make some sense of. And we'll go into detail now. So before I do that though, the question is, what do these numbers represent? Do they represent the water concentration of minerals in the deep mantle, which is what we would hope they would, or do they reflect the water activity in deep diamond forming fluids? And I hate to say it, but it's probably the latter, because Andy Thompson, who did his PhD thesis on all these inclusions, has found that these inclusions plot in between kind of pyroxene or peridotite and eclogitic end members. And so therefore, the only way he could make the major element composition would be by reacting the mantle with the diamond forming fluids in sort of a back reaction. And so he's made the case in papers that what we're looking at are not absolute samples of the mantle, but samples of mantle minerals that have reacted with these fluids. Now, that doesn't mean that all is lost. What that means is we can still use this understanding to maybe set limits on what the water carrying capacity is of these phases, which we then can use to to probe how much the slab can bring down and how much could be in the transition zone. There's other considerations and things like this. Do we have water that's in the inclusion as precipitated at 600 kilometers or 700 kilometers? Or when these things come up and they re-equilibrate and unmix, is this really what's trapped in the lattice at 300 kilometers? And it's probably something in between, and probably the jury's out because we don't have enough analyses yet to really know for sure. And then another worry is, has there been water loss at grain boundaries? That's a potential problem. But what I'm going to show you in the next few slides is that the data we have makes some sense with regard to experimental measurements. And so I think we're actually seeing significant information on water content. So let's look at the Majorite in detail. Majorite is a silica-rich or clinopyroxene-rich kind of garnet that you find at high pressure. And so one individual Majorite with no exsolution was fairly low. And the Majorite where we had clinopyroxene exsolution was a little bit higher, but the clinopyroxene had most of the water in it, suggesting that these kind of numbers for Majorite are real numbers, and we just didn't see any clinopyroxene exsolving from this particular Majorite. Here's another example. Again, here's the Majorite where the clinopyroxene exsolved from it. So it's 40, 50, 50, 80, 30. They're all in the same range, whereas the clinopyroxene has most of the water. And you can see that here in this particular slide, where the clinopyroxene has the higher water signal here in 17 OH. Now, what does that 4,200 ppm mean? Well, we don't really know. We don't have a bulk analysis of that grain. We have a slice through it, and when you do a modal analysis of the mineral proportions, you don't know where you're cutting. We don't know what we got cut off. We don't know what's below our plane of investigation. But if we just use the measured surface areas and the proportions we see, and you make the calculation, you could have about close to 700 ppm water in the recombined Majorite, and it could be almost up to 1,000 ppm. And that's actually very close to, when you take Majorite up to high pressure, about 0.1 weight percent, which is very, very typical of what you would expect if this was the right carrying capacity of Majorite for water. Let's look at the perovskite. So these are calcium silicate perovskites and calcium silicate titanium perovskites. And here's the grain here, again, flipped. Now, it's a very heterogeneous grain. This is a bedellite. This is zirconium oxide exsolving out of this particular grain. And when we go and look at the water is concentrated in hot zones around where you have the phases that are exsolved. And so you can see that there was enough cerium in this particular perovskite that I could actually see it on the electron microprobe. So that's an electron microprobe analysis for cerium. And cerium is a proxy for water, and you can see the water cerium, as cerium goes up, the water content goes up. And so we think that actually these water contents are preserving some original vestige of their water, and it's pretty high. Okay. Now, an interesting wrinkle in the data that no one understood and we still don't really understand, but it's something we have to grapple with, is Coesite. Coesite was completely ignored in the suite of diamonds, but it was in almost every diamond. We kept looking at the Coesite, and Galena said, "Oh, silica's not interested. It's interesting. It's not interesting. Nothing fun going on in silica." The Coesite should have a very nice substitution mechanism that involves aluminum 3+ with water substituting for silicon 4+. And that's been studied a lot experimentally, especially in stishovite, although I'm saying this is Coesite at high pressure, but in stishovite it's been well studied. And you should expect some sort of substitution that would give you an aluminum to hydrogen ratio around somewhere between 2 and 7, as shown by Litosov here, probably work they did at the geophysical lab. What's interesting is we were able to get really good, because of electron microprobe quality here at Carnegie, we were able to get really good alumina concentrations, even at low concentrations, and it scales really well with water. So here's the alumina water right here, but it's way off what you would expect for the normal substitution mechanism. So this suggests that these coesites are completely different from the other minerals, and they have another problem is that they really So they're really undersaturated with regard to water. And secondly, they shouldn't really be in a mantle that is silica undersaturated. So what is excess silica doing in a diamond in a system where free silica is not expected? So this is something that we have to work out. But we think it means that the perigenesis of the coesite is completely different, and it might be more related to the fluid at its last gasp than let's say these other mantle phases. So just to complete the story, I want to compare what we've done to the other estimate for water in the mantle. And this is always a slide that gets a lot of laughs because people know this paper. This is Graham Pearson's work, a former DTM postdoc we all know quite well. So here's a real, ratty, nasty diamond. Graham decided that, when he was interviewed for this, he said that this was a really hard thing to do because working on these diamonds were hell. You can't see through the diamond. And so the Register picked up on this and they decided to really amp up the headline. Satanic hell diamond tells of sunless subterranean sea. Scientists get answers from green gem inside ugly sparkler. And the funny part of the story is Graham didn't know they had a ringwoodite in there because he couldn't see it. And fortunately, the day that one of his students was going, just going, through tray after tray of diamond and looking through the diamond, and Luz Nazdala, I think it was in the lab. He said, whoa, stop, and he said, I think that's a ringwoodite. And Graham's like, what, and so then they worked on it for 2 years and got this unbelievable result where they kept the ringwoodite inside the diamond. They used the diamond as a container and looked through it, did a lot of spectroscopy, and in the end they were able to convince themselves that they had about 1.5 weight% water. Well, the Alberta publicity department just went crazy over that, and they published this publicity thing. They got waves here in the transitions and ripples, and they just went crazy on this. But for about an hour, about 2 years ago, this was the number 1 or 2 story in the internet worldwide. So it goes to show you, if you find something, like a lot of water in a diamond, it can make good press. I mean, the point is, here's the upper limit. This is not as much as ringwoodite could take, but it certainly suggests that high water contents can be seen in these minerals that are forming from recycled material in the transition zone. Now, how does it compare to the lithosphere? So recently, in 2015, David Novella, who came here as a pre-doctoral student working with Eric, and Fabrizio Nestola, who I just showed the X-ray diffraction work of, published a paper in Litho. It's a very short paper. And they did what I think is a really great experiment. They took bona fide lithospheric diamonds, beautiful, here's a beautiful octahedra with some really nice olivines in there, and garnets, and they said, okay, what would be the water content if these super deep diamonds are supposed to be wet, and we think the lithosphere is supposed to be dry, let's check and see what the water content is of lithospheric minerals. And so they've got 2 garnets they've worked on, essentially 0, below detection limit. They had 7 olivines, and they were less than 5 ppm. So this is way below what's seen in olivines in xenoliths that come up in kimberlite. And there's quite a story in stabilizing lithosphere that's based on how dry it is. And Anne Peslier, who's Al Brandon's wife, and Al Brandon is a former DTM postdoc. Anne Peslier made her career recently on talking about water content of xenoliths from the lithosphere. But they're all much higher than this. So what this suggests is that the indigenous water content of depleted lithosphere is really low. It's captured by being encapsulated in diamonds, and the higher water content of the xenoliths that are brought up by kimberlites is actually water added during the magmatic transport, and probably in channels that are associated with the access of the fluid to the lithosphere. So that's actually kind of a nice sort of side comparison to the wetness we see in the transition zone and super deep diamonds. So if we put it all together here, here's your lithospheric shallow stuff that's above about 200 kilometers. This is the phase diagram for the this is the mineral portion diagram for the mantle. So this side of the mantle diagram is the perotitic side. This side is the basaltic side, or the eclogitic side, and this is after a figure of Ben Hart's. And so the olivine and the garnets are really dry, and of course that's associated with the dry lithosphere. As you go down in the mantle, the majorite that's dissolving, or the clinopyroxene is dissolving into the garnet to make the majoritic garnet is wetter, but still drier than when we see the majorite down lower. And of course we have calcium perovskite here, which is one of our major water carrying phases, as it is with other incompatible elements. And of course the ringwoodite, which has been talked about for a long time as being an anomaly anhydrous mineral that stores a ton of water, is in fact storing a ton of water. So we're going to be working over the next couple of years to fill out this diagram and see what the variability is, and try to put together a better picture of getting water down deep. With that, I'll end. Here are my conclusions. That the analytical data in the water part anyway, the analytical data makes some sense relative to experiments, and this suggests that we have some systematic retention of water, that we haven't lost a lot of it even during the polishing. Since these phases are reaction products from the diamond forming fluids, water content reflects the water content of these fluids more than it does the ambient mantle. But we can use that data to set limits on what the water content of these phases would be. The data suggests that slabs do transport water to the transition zone, lower mantle, and that the Hartsbergitic part of the slab is perhaps the most important. And then we have some water-carrying minerals that are undersaturated, such as this coesite, and either they have a different paragenesis or from drier parts of the mantle. And I think the future looks really bright for, this is a very confusing looking diagram, but it's suggesting that diamonds are forming in lots of regions of the mantle, and as we start looking at more and more of them, we're going to have really a much better understanding of what's going on well below the lithosphere. I'll stop there.
Go ahead.
I have a question. So, you studied maybe the space scale from the top to the depth, the deep mantle about the water content. Have you saw that maybe the water content through the Earth's history of the mantle changed?
Yeah, I mean,
the time scale.
that's a very good point. We don't have a good age handle on the diamonds we're looking at that are coming from real deep. And I don't know if we're ever going to get, given how difficult it was to get that one sulfide and how, not squirrely, but how variable the big error in the model age, that's going to be a very difficult thing, because almost all the old diamonds that we see are from the lithosphere, and they're not going to be, from the super deep paragenesis. So that's going to be a very tough one. We'll have to maybe figure it out from the petrology of the lithosphere and its evolution more so than, actual diamond analyses, I think.
Okay.
Okay.
So the water content proofs in Coesite and Monica, when she was here and we studied the solubility of water in Coesite, what we find is below 5 GPa there's no water content, and that's consistent with old metamorphic Coesite. It's basically very dry, only about 5 GPa.
Okay, cool.
See some solubility, but it's not unsaturated water. It's not really, it's probably limited by the solubility of water in Coesite. Basically, all the high pressure ones, the maximum solubility we're seeing is below 100 ppm, and it doesn't matter how. But the stishovite is a different story.
Right. So would you, if you look at this data, would you think that this has lost its water?
No, it's just there's pretty much showing is definitely above 5 GPa, but has the maximum solubility of water already in the Coesite.
Okay, so I need to go over and talk to you about this data. That's great.
Steve, the -25 signal for the diamonds is as a signal of biological carbon. Are there any other mechanisms that could explain the -25 signal without biology?
Well, there are people that have experimentally studied the fractionation question, and you can get isotopically light carbon. If you go to extremes of fluid versus diamond percentage, or if you torque the system, But if you actually try to do something that's geologically reasonable in terms of the fluid composition that's constrained by the type of things we see, I don't think at those temperatures you can't get as much fractionation as down to there. Minus 25 is very common in this set, but you also have diamonds that have minus 40 for isotopic like carbon. So I think the community feels right now that you've got 3 or 4 per mil kind of variability that might be due to fractionation between the fluid and the growth during growth, but probably these extreme values are source related. So I'm definitely on the side of claiming it's from an isotopic like source.
Remember Claude Legg's famous statement about you want to be buried in the subduction zone so it could be subducted and turned into a big diamond?
Where did he say that?
Oh, it's some meeting.
Yeah, so this may be a naive question, but do you see any chlorine anomalies associated with these?
Chlorine isotopic anomalies?
No, just abundances. Do you see any enrichment in chlorine associated with the water content?
Yeah, so gem diamonds have lower quantities of everything because that's why they look so nice. And recently Graham and his group published a paper, and Jakob Weiss at Columbia, where they got really nice chlorine contents out of diamonds that are almost gem quality, that are relatively young, or actually they're fibrous diamonds, and it was on the cover of Nature. So I think the connection between the really chlorine abundant fibrous diamonds and the gem quality diamonds is one that the community is starting to make now. And recently Oded Navan did a really interesting experiment. There's a type of twin diamond called a mackle, which has 2 diamonds twinned that form along a twin plane, and they looked really hard to find along the twin plane tiny inclusions to see if they looked like they could find fluids in there, and they would look like the fluids that you see in the fibrous diamonds, and they do. And so now the community is kind of thinking that the gem quality diamonds may form from fibrous, from fluids like the fibrous diamonds form, but they just grow over time to kind of get rid of those. So I think the answer is yes, but we don't have good data, good hard data. It's not straightforward. Doug.
I was hoping you were going to tell us about a sulfur 33 anomaly in the sulfide, but it sounds like you just kind of ground it all up.
No, we have pieces of it. So
because James's work on the 1270
right.
at UCLA, it pretty much, well, the carbon 13 of course is very indicative, but the sulfur 33 anomalies are really quite well. Can you explain to accept that those rocks were once very, very much at the Earth's surface?
Right. So we have some small pieces. Like we have pieces 4, 5, 6, and 7, which didn't get little tiny slivers as the thing broke apart. This is actually piece 1, which was the big piece, and so Karen and I talked about that, but we haven't taken it any further. So is James actively doing stuff not on the ion probe, but in his lab that's this small?
Oh no, I don't think so. You'd have to do it.
Yeah, I'm doing that.
I
Okay.
presume that your NanoSIMS will do sulfur. I don't know.
Well, you got to tune up for it.
Yeah, well,
we could do it. But that's a great suggestion.
Zach?
Is there a way to look for more ringwoodite grains in diamonds based on anything special about this particular diamond?
Yeah, so every one of these diamonds has like a horrible coating on it, and you have to cut windows in them and look. So we have to get some student and pay them slave wages to actually put windows in every diamond. I like to have 400 of them, and they have junk in there, okay? But it's really, like when Vincenzo Stagno was here, before I went to Japan, he said, Steve, could you just give me a diamond with an iron carbide inclusion in it?
Sure.
And I said, yeah, here's a pile of diamonds, figure out which one it is, And so yes, I think there'll be lots of people finding more of these, but it's really brute force. You got to sit there and go through them. And Steve is sort of smiling. He's kind of smiling knowingly when I say this. Yeah.
Have you considered doing micro CT to look inside these things, and then you don't have to polish them? Things will just jump out, especially sulfur.
Micro tomography, you mean?
Yeah.
I hadn't thought about it too much. I mean, can you do mineral identification?
Certainly things like sulfides. Yeah.
Okay, so we should talk about whether that's a good way to screen them. Yeah. Do we have? We don't have a micro. We don't have a micro unit here, do we?
It's the X-ray method is just limiting the resolution. Actually, what's his name? We had a postdoc in here talking. Basically, it depends on how small you want to go.
You just get mean atomic density too, don't you? And it just shows shadowing into
Yeah,
molecules.
yeah. You can identify that.
I mean, it comes down to how much of it's a research, technique, or how much is a screening technique. That's the problem, because we have a lot of specimens to look at. There's a lot of stuff in there. Glena's method is to just optically cut a window, optically look and say, "Ooh, this looks interesting." Polish down to it, see what it is. But that's, she's just doing that all the time. It's just.
You can calibrate the grayscale on the CT tomography to give you some rudimentary mineralogy.
Okay.
A CT scan of a small diamond, and the resolution depends on how close it is to the source, but it's 20 minutes.
Well, it would be great if we could come up with a better automated way to do it, because I'm sure there's lots in the diamonds we have. It's just going to take forever to look through them. Dan.
So I'm curious about how this layer of oxide formed on the sulfide grain. Because that was apparently, it was in situ, right? It was within the
Right.
diamond, and so you had a fluid that was oxidizing enough that you could preserve this layer of oxide, and simultaneously reducing enough that you were crystallizing diamonds. So, are there ideas about how that happened?
Well, I don't think that's an in situ thing. I think the grain grew, and I think the diamond must have had a crack in it. That was sometimes these cracks are difficult to see, or they're healed, and when you do this kind of work, you look, very carefully. Steve and I were looking at a grain yesterday from a Letseng diamond, and we thought we had everything perfect, but then there's a little place where the fracture system, intersects the surface. And if you've got any of that going on, you have pressures and temperatures where then you're suspect. You're worried. And we didn't like the texture not the texture, the color. It didn't look brassy. It didn't look like a sulfide. It looked black. I'd never seen that before. Although the fracture system, the sulfides usually fracture the diamond from within. That's very indicative. So what the model would be, you have that grain, that's an original grain, and then at some later time, I don't know how close to the surface, this fracture allows fluids that are either associated with the kimberlite, probably not that, maybe even later, to get in. These are alluvials, so they're not going to be stuck in situ. They're going to be, well, no, this one was actually in the kimberlite, so that's not true. But we don't know how long it sat on the top of the kimberlite weather. That's also a problem.
Any other questions? If not, Steve's been here 30 years. He's going to be around for quite a few more. He's available for conversation. Let's thank Steve.
Not mine. No. Yeah, Stanley's. That's what I got.
The other night.